Hi.
Hi.
Hello. Can you hear me? Okay.
Yes.
Yeah.
Perfect. I can hear you both, so that's good. Thank you for taking time out of your weekend and doing this with us. It's going to be really fun.
Nice. Yeah. Thanks for organizing it.
Of course. I was just about to just type something in the chat for everyone to remember to join. Do you want to just check to make sure that your screen sharing is okay?
Sure. Yeah. Do you want to start it, Isabel?
Sure. Everyone can see it?
Yeah, perfect.
Great. Sounds good.
Are you still able to see the hop-in screen?
Yeah, I can still see the rest of it.
Okay, perfect.
Yeah.
And I'll be here the whole time in case there are like questions or something also.
Yeah. So where did Kelly go?
Sorry? Oh, I'm so sorry about the notifications.
Oh, no, you're good.
It doesn't stop.
I can imagine organizing this must have been so much. This is really cool. Is this like the by UCLA?
Kind of. It's like a bunch of different groups at UCLA, from like the engineering and physics and all the other departments. But it's open to everyone. So like officially our sponsors are UCLA departments, but yeah. How's doing the demos online after everything moved? Was that like an easy transition-ish?
Yeah, it wasn't too bad. We have like a really handy simulation tool, which just made it nice.
That's good.
Am I back? Sorry.
You're back.
Don't know what happened. I got kicked out. Sorry about that.
Oh, you're good. Yeah, we're basically doing this EYU style-ish, but the only issue is not a lot of students came today as much as we hoped. So we wanted
Saturday. I get it.
Yeah.
Yeah. I mean, we were kind of expecting it, but at the same time, it's hard to do it during the week because they have classes and stuff.
Yeah.
You can't win.
Yeah, either way.
Is this the first time this conference has been put on?
Yeah.
Oh, very nice. I think it's an awesome idea. I hope it keeps happening.
Yeah.
Honestly, me too. Let me just move because Hopin always makes my laptop die. So I need to charge it. Sorry.
No worries.
Oh, someone's here. Hi, Karen. Karen's an undergrad physics major with me.
Nice. Hey, Karen.
I mean, we can go through the demo if you want right now. I'm excited to see it.
Sure, whatever. Yeah, whatever works for you. So, sorry, I think when I got kicked off, I missed the piece where there are three separate of these demo rooms going on.
Yeah, and all at the same time.
Okay.
Just so if someone wants to go to all three, they can, make it to all three. But we were thinking of having them, in 20 minutes. In one session each, but then it wouldn't have. I don't know, just gives people more access to like go to the one they want in the moment they want,
Yeah.
But they were just happening at the same time, and whenever they join in, the kids, like you can, I guess, redo it because it's just me here.
Sounds
And yeah, it goes till 2, and then after 2 we have like a tea time hour. So you're welcome to like join into the community rooms under the sessions tab if you want to chat with people and stuff.
nice.
We also know it's your weekend, so you don't have to at all.
Cool. Isabella, do you want to start with the slides, or do you want me to start with the?
Sure.
Yeah, go for it.
I'll try switching off. I'll pull these back. So for the demos today, we wanted to kind of like frame it around major contributions that women have made in astronomy. And so in our simulation software, Kelly will show a bunch of different ideas, and I just wanted to mention some of the background about the women who came up with these ideas and made those contributions to astronomy. So the first thing we're going to look at is we're going to talk about stars and how we can classify them. And a ton of this work, well, really all of it, was sort of started by Annie Jump Cannon. She completed her education at Wellesley, and then she actually took like 10 years off to just travel and pursue arts and stuff. And then she decided to come back to astronomy. She took a job at Harvard Observatory, and her job, as you can kind of see in this lower picture, was basically to like manually go through lots and lots of different images and spectra of stars and figure out a good way to classify them so that we can kind of learn a little bit more about why there are different types of stars and where all those come from. So she looked at thousands of stars over the course of her career, and she came up with this really great way of classifying them, which is a scheme that we still use today. Over the course of her career, she eventually was put in charge of managing all of this collection of different astronomical images. She was also the first woman to get an honorary doctorate from Oxford, which is super cool. And there's still an award in astronomy named after her. So every year, an outstanding early career astronomer will still get the Annie Jump Cannon Award. Okay, so I'll close mine, and then Kelly, you can share.
Alrighty, let me know if it's up. Can you guys see that all right? Okay, cool. So yeah, just to highlight some of the things that Isabella just told us about the contributions from Annie Jump Cannon. One of them was, or this main piece was characterizing stars in a way we still see them today. So right here in this simulation, we have just a simulation of a lot of the stars that are around the sun. Pretty much picked out the stars, the brightest stars that are around the sun. So if we have the sun here in the middle, if we zoom out, we just see, all these other stars in the sky that are anywhere throughout the Milky Way galaxy. And it's really hard to classify them because they're all at different distances. They're all at, they have, different masses, different temperatures, different radii. And so one of the things that Annie Jump Cannon did was figure out how we can look at these in a reasonable, or like understand kind of what each of these stars, the different properties of the different stars mean. And so here we're just looking at all the stars we were just looking at in the sky. We're looking at them in order of mass. And you can see that, so starting with the left is the most massive on the left. And you can see that the most massive one is not the one with the biggest radius. And so this is kind of what I mean, where it's difficult, especially in early astronomy, to classify things. And so if we then look at temperature, you see that the the order of all of the stars that we're just looking at changes. So actually now the hottest is on the right here, but the biggest one is on the left, which is the least hot. And so what Annie Jump Cannon did is basically characterized stars in order, or classified stellar types by temperature, which turns out to be super useful. That is the convention that we still use today. And this, what's shown on the screen here is called the HR diagram. And that is like probably the most fundamental chart or plot you'd see in astronomy if you take, astronomy classes. And this, comes, oh, sorry, it zoomed out. This comes from her. And the cool thing about characterizing stars by temperature is that when you look at it in this way, it allows you to see what part of star's life the star is in. So just in this diagram here, basically the brightness is on the y-axis, so the bright, and on the x-axis you have the temperature, where actually temperature increases to the left. So it's a little funny in that way, but it allows you to say, okay, if you see where a star lies on this plot, then you can see what type of star it is and where it is in its life. And basically what Annie Jump Cannon did is define like these, I don't know if you can see my cursor, but like this side of the plot, the left side is say O stars, and then each one has a different letter, and they're the different letters, are boxed across the x-axis. So yeah, and I'll stop sharing my screen to give this back to Isabella to tell us about our next highlight.
Well, I think you're muted.
Stars are really important when we think about what space is made of, but there are lots of other components which we also need to know about. And one of those components, dark matter, was really proved by the work of Vera Rubin. So she had a PhD from Georgetown, and kind of her major contribution was to take a bunch of measurements of spiral galaxies. So she would basically look at the stars in spiral galaxies and see whether the stars on the inside of these galaxies were rotating just as fast as the ones on the outside. And before this, there wasn't really an expectation that they should rotate at the same speeds, but she found that they actually do. They called this the Rubin-Ford effect. And this finding that the centers and the outsides are rotating at the same speed proved that there needed to be dark matter in these galaxies, kind of keeping everything going. And this was something that had been proposed, but a lot of people didn't really believe because there wasn't the evidence until all of these observations were made by Vera Rubin. So she looked at many, many galaxies over the course of her career. She has an asteroid and a telescope named after her. So the telescope on the right, kind of in the works. And close that.
All right, so this is showing exactly what Isabella was just talking about. We're looking basically face on at a spiral galaxy. So the Milky Way is an example of the spiral galaxy. This is not the Milky Way, but something of the sort. Whereas Isabella mentioned, that the outside is moving as fast, basically, as the inside, and that is what Vera Rubin discovered. If we zoom in here a little bit, you can see how it would be confusing that the stuff on the outside edge is rotating as fast or faster than expected, because we see most of the light is in the center. And so that's why it was really revolutionary and led to this discovery that there is dark matter in these galaxies. And just to show another fun view of it, here we're looking edge on at a spiral galaxy. And so when we look, up in the night sky, and if we're in a clear place that's not LA, desert or mountains or something, you see the strip of the Milky Way across the sky. That's because we are in somewhere, around here in the outskirts of the disk. And if you're looking through the disk as such, it would look basically like a band across the sky.
Sorry, my sharing options got limited to YouTube video. I don't know how to bring that back.
Oh.
All right. Okay, never mind. We're good now.
Okay.
That's kind of weird. Great. So now that we're talking about galaxies, one of the people who made huge contributions to how we understand galaxies is Sandra Faber. She's actually still in the field. She's working at Santa Cruz and an observatory. But she got her PhD from Harvard, and a lot of her work focused on if we can write these relationships between different parameters of a galaxy. So she looked at things like the brightness of galaxies and how that should relate to how fast the stars are moving around inside the galaxy. And she came up with this relation that we call the Faber-Jackson relation, which is very, very widely used still. In addition to all this, she also did lots of cool things with dark matter. She came up with kind of new theories of how to think about it. She's also led a bunch of teams. So one was to set up at the the Keck Observatory, and she was involved in kind of a lot of planning on that side, which of course Keck has just been a huge tool to everyone since it was first established. She also, and I didn't know this before, but she also led the team that helped to fix Hubble's initial optics issues. So there was a big problem with the Hubble telescope's optics that made images look not so great, and she helped figure out how to fix that. She has a National Medal of Science, and again, as I mentioned, she's still doing lots in the field, and with Lick Observatory, there are many opportunities for grad students currently to kind of go and learn more about observing and astronomy research. Okay.
Cool. So yeah, as Isabella mentioned, Sandra Faber had a lot of really huge contributions to astronomy, one of which was this, what's called the Faber-Jackson relationship, which helps classify and relate properties of different galaxies. So we just looked previously at spiral galaxies, and they, one of the other main types of galaxies is elliptical galaxies, and that's kind of what we're looking at here, which are unlike the spiral galaxies, which we saw moving in a coherent direction and looked more like a pancake. This, as you can see, if we go around to different angles, it's more of a fitting to its name, more of an ellipse, or not a pancake. And so one of the things she did was to relate basically how bright an elliptical galaxy would be related to, and relate that to how fast the stars within it are moving. And that is, as Isabel mentioned, yes, so super widely used, and is one of the few laws, so to speak, of astrophysics that is widely used that's named after a prominent female astronomer. And as I switch my share here, sorry, I just got muted. The contributions to Keck Observatory that Isabella mentioned, that Sandra Faber was instrumental in, kind of leads to now our next highlight.
So I think you all actually heard from Andrea before, so I probably don't need to say a whole lot more about her. But this finding that she had of measuring this supermassive black hole at the center of our galaxy really like fills in a third big feature of galaxies. So they have stars, they have dark matter, and there's this huge like powerful black hole at the center that can also just influence the physics that you have in your galaxy. She studied at Caltech. She did these observations, as Kelly mentioned, at Keck. And along with, just measuring the stars and their motion, there's also a ton of physics that can be done with this information, right? There's a lot of aspects, for example, of general relativity that you can confirm by really digging into these observations around the black hole. And very recently, she became the fourth woman to receive a Nobel Prize in physics, which is really incredible.
All right, and this simulation highlights a lot of that work that's been done by Andrea Ghez here at UCLA. What we're looking at here is the projected orbits of a lot of the stars around the supermassive black hole in the center of the galaxy. So obviously the lines here are just to show you where the orbits are. You could look at it, without that, and you just see over time that, very, very close in, you see over time that there's these stars that are moving around like, some coherent center of mass. And that is what initially proved that there is a supermassive black hole at the center of the galaxy here. And as Isabella mentioned, that's been used to, that's been, an ongoing project. It's been, over 2 decades long of observations to get these orbits. And here, just zooming into this artist's conception of black hole is showing us that if you get really close in and if you can observe precisely enough, you can see how the star's path and light is bended by the black hole in the center. And so that is what basically what was done over the past few years that led to the Nobel Prize work, where it was shown that the supermassive, or that general relativity was held up against this test in the proximity of a supermassive black hole, which are the most massive things that we know of.
Question, if that's okay.
Yeah.
So the closest star, or the closest orbit to the black hole, how long is its period?
That's a really good question. So the closest star that we have observed a full orbit for is 16 years. There are stars closer, but they're so close that the telescope can't resolve them or differentiate them between the light that's being splayed out from the being like ejected from the accretion around the black hole. And so actually we can zoom in on it. SO2 is this blue star here that's moving in the center. And so 16 years is how long it takes it to go all the way around, which is actually really remarkable given this thing is 25,000 light years away and in a observable lifetime, you can actually watch it go all the way around is pretty crazy.
I think you had a question in the chat as well from Natalie. What causes the star's movement to speed up in certain areas of their orbits?
Oh, that's another good question. So that happens because of where the black hole is. So if we look at this more face on, this is actually how it was found out, like where where the black hole is, because if the star is closer to it, it's going to be moving faster because the gravitational attraction is higher. And so the black hole kind of forms, or is the center of mass of all of these orbits, and you can see where that common center of mass is. And so everything, and again, I don't know if my cursor is super visible, but everything around where my cursor is here in the center is where it's going to be moving faster, or any of the stars that go by are going to be moving faster around there than further out. And they all have, different shapes, so the speed that they change would vary depending on their shape or how elliptical it is. And yeah, I think that's what we wanted to showcase. Are there other questions?
More in the chat. Elliot asks, what's the star called, the one that orbits in 16 years?
It's called SO2. They have, as most things in astronomy, just seemingly random names with letters and numbers, but yeah, SO2.
Everyone can also ask questions in the Q&A if you prefer to be anonymous, or in the chat. Both are okay, of course.
And I didn't see also when different folks logged in, so let us know when, Sarah, if you want, we can start from the top or whatever.
A bunch of people just joined in. If you want to restart it.
Anyone coming in? We're showing some demos of different ideas in astronomy. And we're kind of framing this around the contributions that have been made by several female astronomers. So the first idea that we're going to show is something that was invented by Annie Jump Cannon. So she was an astronomer in the late 1800s, early 1900s. She studied at Wellesley, and she eventually had a job at the Harvard Observatory where, if you can see in this bottom picture, her job was basically to manually go through the spectra of lots and lots of stars and pick out some of their properties and figure out a way to classify these stars. So over the course of her time at this observatory, she looked at thousands of stars, and she came up with a really great classification scheme that we still use today. Over the course of the rest of her career, she eventually was put in charge of managing this collection of photographs. She was also the first woman to get an honorary doctorate from Oxford. And we have an award named after Annie Jump Cannon now. So every year, early career female astronomer who's doing a great job will get this Annie Jump Cannon award. So her name lives on in this way as well.
Yeah, so as talked about, one of the major contributions is how stars are classified. And so right now, what we're looking at is just a bunch of stars that are near the sun, basically just picked out the brightest stars near the sun. So we zoom out a little bit, we can see kind of what we would see in a normal night sky, just a bunch of stars that are as big or bigger than the sun, but look, very tiny, very far away. And we can look at them we can classify them in different ways, and or order them in different ways rather, which makes it really difficult to classify them because they have so many different properties. And so that's what is really useful about Annie Jump Cannon's work. So here we're just sorting all of these stars that we were just looking at into order of decreasing mass. So on the left-hand side is the most massive stars, and on the right goes to the least massive. And interestingly, you could see that the biggest one is not the most massive. And similarly, if we sort in terms of temperature, the size of the stars and the color, etc., all changes. So how do we how are we able to actually classify what a star is, where it is in its lifetime? And that leads us to what's called the HR diagram, which is one of the most fundamental plots or diagrams way of visualizing stars in astronomy. And this was a huge contribution from Annie Jump Cannon. She created this classification of stars based on their temperature, which allowed her and now us, is still 100 years later, this is still how it's used, to draw out these relationships where, so what's shown here is if you were going along the x-axis, the left-hand side is hottest, and as you go to the right, it gets cooler and cooler, and then as you go from the bottom to the top along the y-axis, it gets brighter. And so you can bin all of these different stars into different temperature bins, and that allows you to tell where a star is on this diagram, and therefore what type of star it is, and what type of elements are in its atmosphere, and where it is in its lifetime. So that is a really substantial contribution that is still used very much.
So our next simulation is going to show an idea from Vera Rubin, who was, she got her PhD from Georgetown, and her major work was to look at spiral galaxies and to measure how fast stars are rotating in spiral galaxies. And so until this point, there wasn't really a reason to think that everything in a spiral galaxy should be moving at the same speed. But she found, as she was really carefully measuring these galaxies, that in fact, the stars at center of galaxies are going around the galaxy just as fast as the ones on the outside. And this particular finding was one of the main reasons that we could prove that dark matter is existing in these galaxies. Up until now, there wasn't evidence for it, and so people didn't really take the idea of dark matter all that seriously in astronomy. So this really changed, how we think about galaxies and how we think about the composition of the universe in general, in a huge way. So she looked over at over 200 galaxies in her lifetime. She had an asteroid named after her at one point, and there's actually a huge telescope in the works also named after her, which should be doing great things for future observations as well. Okay.
So this is a depiction of a spiral galaxy, showing exactly what Isabella just talked about, how the rotation of a spiral galaxy allowed Vera Rubin to discover the idea that there is dark matter in galaxies. So this is a face-on view of a spiral galaxy. And you can see it's kind of more populated with stars in the middle, so brighter in the middle. And that's why it was such a surprising thing for Vera Rubin to find that stuff was moving faster than expected at the outside. So that means it must be moving because of stuff that is not seen, right? Otherwise, if you just looked at the stars that are there, you'd expect to be rotating differently. And so just for fun here, we can look at just different angles of this spiral galaxy. And so if we go to like an edge-on view, you can see a spiral galaxy is kind of like a frisbee or a pancake in a way, has a more flat side. And that's what, since we are somewhere out in the outskirts of the Milky Way, which is a spiral galaxy, that's why when we look up in the night sky in somewhere where we can really see the stars, where there's not a lot of light pollution, you see that band across the sky. That is the disk of the Milky Way.
So on the topic of galaxies, one person who made huge contributions towards how we understand galaxies is Sandra Faber. So she's currently at UC Santa Cruz, but she got her PhD from Harvard, and her major work was to look at galaxies and measure lots of different parameters and kind of see how they were related. So she looked at things like the brightness of galaxies, how fast the stars in each galaxy were moving, and she developed this really famous relation called the Faber-Jackson relation, which we still use quite widely today to understand what's going on in a galaxy. Aside from this, she also did a lot of cool work, again, in dark matter. So she proposed this kind of new way of thinking about dark matter that we call cold dark matter. Lots of work on galaxies in many different aspects. Aside from this work, she's done a lot of really cool projects within, like for observatories in astronomy. So she led a team that helped establish the Keck Observatory, which Kelly will talk about why that's important in a little bit. And she was also on a team that helped to fix some of the initial problems that were occurring when the Hubble telescope first launched and was trying to take images. So two really cool projects that helped us learn a ton since then in astronomy. She received a National Medal of Science, and again, she's currently still in the field, working at Santa Cruz and at the Lick Observatory, which is really useful both for science and has been a really great tool to train grad students and younger students as well, just in how observations are done and how research works.
So to show a depiction of one of the highlights that was just talked about, this is an elliptical galaxy, just to contrast what we were looking at before, which is a spiral galaxy. This is basically just a big clump of stars. And we could look at it from different angles, and you can see there's not an angle at which it's just totally flat. And so Isabella mentioned the Faber-Jackson relationship, which is a key way that these type of galaxies, elliptical galaxies, are classified. And so you see, like, the stars in the galaxy are all moving with respect to one another. And so she was able to identify a relationship between how fast those stars were moving and how bright the elliptical galaxy actually is. And yeah, again, that's still widely used rule and one of the few laws of astrophysics that's named after a prominent female scientist. And as we switch screens again, just to lead into the next person that we'd like to highlight, I want to touch on Vera Rubin's contributions to building Keck Observatory that Isabella mentioned, because that is kind of the legacy lives on through Andrea Ghez, who's been really instrumental in developing the science cases that have driven further development of Keck Observatory.
Yeah, so our last demo is going to focus on Andrea Gez's work. You all saw her, I think, maybe a couple days ago, so just a couple reminders about what she did. So she has a PhD from Caltech, and using Keck, she observed a lot of the stars that are at the center of our Milky Way, and by really carefully following their orbits, she was able to show that the motion that they follow proves that there needs to be a supermassive black hole at the center of our galaxy. So that's really important because supermassive black holes can have a big effect on the galaxy as a whole. And so they kind of fill in, a third aspect of galaxy features. So we have stars, we have dark matter, and now we know that there's this black hole that will also be affecting things. The physics kind of behind this is also really important because in looking at black holes and kind of confirming different aspects of them, it confirms a lot of aspects of general relativity, which is always good to make sure that it's still working. Aside from all of this, she was the 4th woman to receive a Nobel Prize, which is really wild and awesome. And again, all of her students, like Kelly, are still continuing all of this work.
So here we are now looking at a zoom in of the center of the galaxy, and this is just a simulation of the stars that are orbiting the black hole in the center of the galaxy. And this is what was initially used to confirm that there is indeed a black hole there. So if we turn off the trails to show the orbits, and you just see the stars here, we see that they're all moving oddly around some common center of mass, and they're not just like in the last picture that we looked at of the elliptical galaxy. They're moving in different directions. Here we see that there is this odd thing in the center that causes the light and the path of the stars to bend as they go by, and that is what was just tested in the most recent test of general relativity around a supermassive black hole, which is basically the most massive objects that we know of. And I'm just going to zoom back out again so we can look at a further view of some of these stars that are orbiting. And I want to highlight one thing which is really neat is that this work, what has been observed that has led to the ability to actually see these orbits has been collecting data over 25 years, and that's work that Andrea has started and has continued to keep that project moving forward and learn more and more about this really interesting region, the Galactic Center, to learn a lot of interesting physics, like Isabella mentioned, general relativity, and astrophysics, like the evolution of the Milky Way galaxy itself. So yeah, if anyone has any questions, feel free to let us know.
As we wait for questions, I'll just mention that this software that we use, I believe, was also in large part created by an astronomer. And I think it's really cool because it it all works on like real physics that people had to figure out. And all of the kind of objects that are included in this are also real objects again. So that people had to spend years observing and really understanding like where they are and where they're going and what the orbits look like. So it's really cool that we can kind of have this one place that sort of wraps up a lot of the things that we know about astronomy in one platform. And so we can show all these different objects, from stars to galaxies and other things as well.
I have a quick question, just while people maybe come up with their own. I'm also being selfish, but it's okay. So we talked about elliptical and then spiral galaxies also. Which ones are more evolved, or like which ones are further in the past or further away from us?
Do you want to take that, Isabella, or do you want me to answer?
Oh, by the way.
I guess, well, I'll say, feel free to add to whatever I say. It's not necessarily like one type evolves into another. And so there's not this distinct distinction where, you know, one is specifically earlier. Generally, elliptical galaxies are older, and the closest galaxy, the closest like major galaxy to us happens to be a spiral galaxy. But in terms of like distribution throughout space, it's pretty isotropic, or, you know, random in a sense. It's not just like clumps of elliptical and clumps of spiral galaxies. There's other things. The third classification of galaxy, to throw in a fun fact, is called irregular galaxies. And I always just find the naming conventions of things kind of funny in astronomy. It's like, oh, this one looks, it's not spiral and it's not elliptical. So
I think the galaxy naming scheme is also a good example of how classifying didn't really work.
Yeah.
Originally, when they were first classified, people were like, oh, okay, well, then we must start with ellipticals, and then we go to spirals, and then who knows about these irregulars. And so it, like, for a lot of years, people were kind of set in this mindset that evolution went that way as opposed to the other way, which is what we think is probably correct. So classifying can sometimes be very helpful, and it can sometimes be dangerous if you don't do it super carefully. Maybe I'll answer the question at the bottom of the chat, and then Kelly, you could talk more about new experiments with the black hole. But this program is called Universe Sandbox. It's not free, but the people who make it do a lot of like education and outreach work. So I believe there are a lot of opportunities to either like try it or watch it be used, or if you needed it for like classes or something. I think they're open to being contacted for all of those things. But yeah, Universe Sandbox. And then Kelly, the question in the chat was, are there any new experiments coming up about the black hole?
Yeah, that's a good question. So just to, I guess, go back from the beginning, I think what your question might be based on is like, right, first it was discovered that there's a black hole, and then, okay, what are we doing now? We're just watching him go around. So one of the things that was done over the last few years was to show this most recent, the most recent stuff that was done that was recognized by the Nobel Prize, was showing that general relativity, which was this theory devised by Einstein, you know, over 100 years ago, that it holds in the vicinity of something that is as massive as a supermassive black hole, which in the case of the galactic center is 4 million times the mass of the sun. But that was only looking at one aspect of general relativity, and there's a lot of different key components of this really intricate theory that Einstein posed. And so while one of them was proven or confirmed, over the last few years, we're now at the position where we can test the next level of that. And so just looking at, this conception of if the black hole is here at the center, as you see stars coming around it, the basic idea is that its gravity will warp the space that the stars are traveling through, which affects their paths. And so there's two components: the light is affected and the paths are affected. So the piece that was previously done is observing how the light is affected, and now what is now possible, based on having accumulated a few more years of data, it's now possible to look at how the path is affected. So that's what's being worked on now in terms of the orbits. And there's a lot of other research being done too, outside of this kind of key central science question about the dynamics around the black hole, but also just studying the stellar populations themselves, like what type of stars are these that we see in the galactic center? Are they in binaries, etc.? So a lot of different things like that can lead to information about how the Milky Way galaxy could have formed and evolved over time. Great. Well, if anyone has more questions, feel free to type in the chat or ask at any time. I guess in the meantime, do we want to just go back to are there any key parts that anyone wants to see, or Isabella, whatever you think? In the last 10 minutes, we can highlight some of the stuff at the beginning in case anyone new joined.
Yeah, either way. You could show the stars some more. I feel like those are fun to see. While we're here, I remembered a fun story about Vera Rubin. So when she was doing her PhD, she apparently had 4 kids. And so her parents, like when she needed to go to class, her parents would take their kids and then her husband would drive her to class, and then he would just like sit in the car and eat dinner while she was in class. Anyway, random story. Oh, there's a question. Are there any cool theories right now about the creation of the Milky Way and black hole?
Oh, so that's kind of an outstanding question that is why this research continues to be done. So I guess the leading theory, or the question over time that's been really big is like, do black holes form and then stuff attracts to it, or does a galaxy form and then the black holes form in the middle? And so I think one of probably the leading theory of galaxy evolution is that these galaxies and stuff form from big clumps of dark matter. But I wouldn't say, I don't know, feel free to add to the answer, Isabella, but I don't think there's like there's not a consensus.
Yeah, I think the tricky thing about supermassive black hole formation in particular too is that it's different from how you would normally make a smaller black hole, for example, just like having a really large star and then it explodes and then maybe you can be left with a black hole if it was large enough. But for these ones at the centers of galaxies, there's a lot more debate about how you could possibly make something that big really quickly. So there's lots of people studying like how this would happen. Some people think like you have a lot of small black holes and they kind of like keep combining. Other people disagree, and so that's definitely a big point of debate at the moment. Yeah, things that happen early in the universe, I think, are often difficult to really pin down exactly how they happened, because it was a really different environment at the time, and so it's hard to know exactly what was going on. But lots of people try to tackle it through really big simulations with lots and lots of particles. You feed in the physics that you think you know, and then you just kind of see like, does that give you something that looks like the universe that we know today? And if not, you kind of go back and you rethink about the physics a little bit more. So I think that's the main way to attack it at the moment.
Yeah, definitely. And so, yeah, just going back to look at some of the stars, seeing there's a question in the chat. Are there specific places to look for more information about, do you mean about the galactic center stuff in particular, or in astronomy in general? I guess if you want to, well, I can answer if you mean the galactic center stuff in particular. There's one of the perks of this work being recognized by the Nobel Prize is that a lot of like outreach and PR pieces were done to kind of explain to the public what work is going on. So I can look for some links. Oh yeah, nice. Thank you for putting that up. There's some links like YouTube and links and stuff that you can get to from the UCLA Astronomy website, going to the Galactic Center group. I can look for those and put them in the chat in a sec. I guess I can go back to the HR diagram, Isabella, if you want to like talk about that, and I can look for the links to share for Galactic Center stuff.
Sure, yeah.
Or whatever you want to talk about it. It's just, that's a fun, I guess that's a fun thing to like, you could talk about whatever you want.
About things.
I know.
Yeah, I think this is like being able to order the stars in here by mass or by temperature at will is a really cool thing to be able to do. Because it shows how difficult it is to figure out if you're just looking at like a random group of stars, to really figure out like which stars have things in common, or are some of them going to explode soon, things like that. And until like this HR diagram, I don't think there was a really clear way to like intuitively see how stars evolve. But when we look at it this way, if you guys all see like the big line of stars kind of going from top left to the bottom right, we now know that those stars are on the main sequence. So they're kind of in the main portion of their lives. They're sitting around burning hydrogen. And then that kind of group of stars in the upper right are ones that have moved on to another phase. So some of them might be burning helium or things heavier than that. And so they're leaving their main sequence spot and they're kind of all migrating sort of in the same direction, actually, for the next phase of their life. And then after that, they can kind of go in a few different directions. Some of the really big ones might turn into neutron stars or black holes. Some of the medium ones probably end up as white dwarfs. They're kind of in the bottom left, or they would be in the bottom left here. So we can learn things like that from ordering stars this way. And we can also see some cool things, like the stars on the bottom right-hand corner have really, really long lifetimes. Long meaning like in some cases longer than the age of the universe. So those are really cool stars to think about. The ones in that bottom corner are also ones that people are really excited about for exoplanets. These call them like M dwarfs or red dwarfs. So they're interesting for that reason too. But yeah, I think every group of stars on this diagram people study for very different reasons. Oh, you guys have animations. So nice.
Yeah, from that site, you can go to a couple, you know, it'll link to a couple different things that tell you about different aspects of the research that's going on. And then also on YouTube, there's some fun videos that talk about it if you just search, I guess, Professor Gez or Galactic Centers.
Okay, it looks like we're out of time. This was so cool. Thank you so much. I mean, I'm a nerd, so I like this. I don't know about everyone else, but this was really fun to watch. Especially that you talked about, stars and galaxies and all the black holes. Oh my gosh, we covered so much in 20 minutes. It was amazing. Thank you for your time and for coming on the weekend and talking to everyone. We appreciate it a lot.
Thanks for having us. This was fun.
Yeah, definitely. Thanks for having us. It was fun, and it's really neat to be able to look at like the history of these. Were just a few of the prominent female. Obviously, there's many, but it's fun to be able to like you said, trace the history of like what we learned about stars and then galaxies and then our own galaxy, etc. Through this path of really influential females.
Yes, definitely. I've never heard of any of them, which is, I mean, except Professor Gez, of course, which is really surprising, I think, because, these contributions are so big and so essential. Yeah, I'll just remind everyone that our breakout room sessions are open now for tea time, which is for the next hour. So feel free to go there, hang out, and meet new people. We would also like to invite you to come if you can for some time and just chat to people one-on-one. So yeah, there's a bunch of rooms, and the tea time room is where you can just hang out with everyone, and there are specific community rooms also open.